Hi, everybody. Let's start the last lecture. Okay, and I think I should use as an eraser. You remember yesterday I told you that if we have a basic classical simple superalgebra, then we can form G hat, which is G tensor C plus minus 1, direct sum CC, direct sum CD. And I told you that we call it non-twisted affine superalgebra. I just should mention something that sometimes when they want to define this in this way, and this G is a basic classical simple superalgebra, some people say that, okay, it's called an affine superalgebra, of course, not twisted one, but in the classification, the case when G is A and N is somehow different. I just want to mention this one, that the definition in the case that G is A and N is somehow different. Actually, instead of one CC and one CD, we need CC1, CC2, direct sum CD1, CD2. And it is somehow different, but some people say, okay, it's not important, and look at this for all basic classical superalgebra as an affine superalgebra. Okay. And you remember, I told you that we have G hat, that G hat, that I call it L. L is direct sum L gamma, when gamma is an element of R hat. And then we said that if P is a parabolic set, then we have a decomposition for L as L plus P, direct sum L null P, direct sum L minus P, where L plus P is direct sum L gamma, when gamma is an element of P minus P, and L minus P is direct sum L gamma, when gamma is an element of minus P, and L null P is direct sum of L gamma, when gamma is an element of P intersection minus P. And if omega is an irreducible L0 P L null, sorry, it is null, not zero. I was supposed to put it in a big circle. L null P, irreducible L null P module. Then we constructed a module like this. That was, you remember, it was a quotient of a module over N, and in which M is just UL tensor UB omega, and B is L plus P direct sum L null P, right? And N was the unique maximal submodule of M intersecting omega trivially. right? Okay, and now the question is that, okay, you said that if we start with a module over L null P, then we can get this irreducible module for L. But the question is that if we have an irreducible module for L, if we can find P and omega such that that module is isomorphic to this module, and it is very important if you want to classify modules, irreducible modules.
Sorry, I have a question. So the first thing that you pick on the direction decomposition, the first one.
Okay.
This is when you have parabolic partition. What was the difference in the direction decomposition when we have parabolic partition and parabolic set?
You know, this is it's not something related to the parabolic set or partition. Okay. We have this decomposition just because of the structure. Yeah. Okay. But if we have a parabolic set, then we can decompose L in this new decomposition. Right. Yeah. And we just use the elements of this gamma depending on gamma is an element of P. Right. minus B, because you remember when we have a parabolic set, it means that P plus P intersection R hat is a subset of P, and P union minus P is R hat, right?
Yeah, that's right.
And exactly because of this, we can decompose L into L plus, L naught, and L minus.
Right. And LP naught becomes H in the parabolic partition case.
You know, when we have a parabolic partition, P intersection minus is just 0. Yes. Yeah. But in general, we have this as well.
Okay.
Yes. Okay. And I told you for the classification, it's very important to realize that if a module can be constructed in this way or not. We refer to this kind of irreducible module parabolically induced. We call it parabolically induced because P is a parabolic set. And so the question is that if all modules are parabolically induced, and if we can answer this question, say, okay, we can parabolically induce, for example, we have a module. We start with a module. And say, suppose that we are too lucky and we can get P and omega such that M is induced omega P. And again, we can ask, okay, this omega is an irreducible module over L1P. But how about this omega? If this omega with itself can be parabolically induced, okay, and then we can ask this question several times, and what happened at the end? If we can get a module after several times, if we can get a module that's such that that module cannot be parabolically induced. And if a module is not parabolically induced, we call it cuspidal, right? So we start with an M, and finally, if we are lucky and we can get such a thing, and this omega cannot be parabolically induced, then we have a cuspidal module. So if you want to classify M, it's enough to know about parabolic sets and classify cuspidal modules. So the classification is reduced to cuspidal modules, right? And And it is very important in the classification of affine the superalgebra in both cases, untwisted and twisted. And I tell you something about untwisted ones, but the twisted ones are more complicated. Okay? And suppose that G is a basic, classical, simple superalgebra, and is G hat, which is G tensor C plus minus 1. There is some C, there is some C. Suppose M is an L module having a vector space composition with respect to H. Okay. Fix lambda 0 belongs to support of M, right? When lambda 0 is an element of support of M, we get that M lambda 0 is at 0. So we can fix an element of choose V0, a non-zero element of M lambda 0. So what we have, you remember the definition of M lambda. M lambda was the set of all elements of M such that HV is the lambda HV for all lambda for all H belongs to H. So as V0 is an element of M lambda 0 and C is an element of H. So CV is lambda 0 CV. Okay. Now, suppose that M is irreducible. Okay. And look at phi from M to M, mapping V to CB minus RV, in which R is lambda 0 C. Okay? Let's look at this. I claim that this phi is a module homomorphism. Okay? It is clear that phi is the linear homomorphism So we just need to check the module action. And for each x belongs to L, we have phi xv equals, by the definition, it is c xv minus r xv. And here, as c is a central element, we get that it is x cv minus r xv for all x belong to lambda and for b belong to m. For all x belong to L and for all b belong to m lambda, then lambda is an element of support of M. Okay, and what we get, we have x CV is lambda C B, and here minus RV. Okay, and here we have x, it is CV minus RV, which is exactly phi of D. Okay, so we have phi xv equals x phi v, right? And it means that phi is a module homomorphism, right? And it is, of course, of degree 0. So phi is a module homomorphism. Then we can get kernel of phi is a submodule. Kernel of phi is a submodule of M, but M is irreducible, so we get kernel of phi equals 0, or kernel of phi is entire M. And at least we know kernel of phi is not 0 because for sure V0 is an element of kernel of phi, right? Because phi V0 is CV0 minus RV, and it is V0. So that's V0 that we choose in M lambda 0. And CV0 minus RV0, CV0 is lambda C, and lambda 0 C is R. So it is RV0 minus RV0, which is 0. And we know that V0 is not 0. So kernel of phi is not 0, so we get that kernel of phi is M. So what we get when we say kernel of phi is M, it means that for all v belong to M, we have CV equals RV. It means that C acts on M as a scalar. Right? And this scalar is called the level of M.
So kernel of phi is equals to M. This implies
CV equals RV. And we can get,
okay.
Yeah, let me write one more time. C acts on M in this way, maps V to CV. Right? And so this C acts as a scalar. Yeah, Okay, we prove that if we have an irreducible L module having a vector space decomposition, then the canonical element C acts as a scalar. This scalar is called the level of M. And it's interesting because the classification of modules strongly depends on this level. It is very different if R is 0 or it's not 0, right? Okay. And now we have a theorem. Suppose that M is an irreducible L module having vector space decomposition with respect to H. Assume dimension of M lambda is finite for all lambda belong to support M. If lambda is not an element of support M, then M lambda is 0. And we assume that dimension of M lambda is finite for all lambda belong to support M. So we assume dimension of M lambda is finite and the level of M is not 0. Then there is a parabolic subset P of R hat and a customodal module omega over L non P such as M is isomorphic to endomorphism P omega. I recall that we call a module customodal if we cannot get that module in parabolically induced way. It cannot be parabolically induced. Okay, and so, and moreover, we have a customodal module omega over this, and moreover, this P over P intersection minus P is finite. So, and look at this. When we say that P intersection minus P is finite. Let's look at L1P. It is direct sum L alpha when alpha is an element of P intersection minus P. And you remember, dimension of L alpha is finite. Sometimes it is 1, and sometimes it's not 1, but it is finite. L non-P is direct sum of L alpha when alpha is an element of P intersection minus P. And each of these L alphas are finite dimensional. And when P intersection minus P is finite, we have a finite dimensional D superalgebra here, right? And so if you want to know about the modules, irreducible modules, having weighted space decomposition, of course, with this property, it is enough to know modules, irreducible modules over finite dimensional simple superalgebra. Those irreducible modules having weighted space decomposition and dimensional omega lambda is finite. So, and it is something that people did it during sometimes, and it's this helps us to know the classification of irreducible modules over affine superalgebra in untwisted case, and in twisted case we get some results in the recent years. And of course, in the twisted case, the situation is more complicated.
Here, L is an affine superalgebra.
Yeah, L is that G hat. Yeah. Okay. And now I just want to mention some differences between super case and non-super case in some examples. I like to see those differences precisely. Because, you know, we can do this. I said it is an affine Lie superalgebra, and if you start with a Lie algebra, I mean the odd part is 0, you get an affine Lie algebra. And all of these theorems and material are satisfied for this
affine Lie algebra mean?
Sorry?
Affine Lie algebra, what does that mean?
Just instead of starting with a basic,
okay.
Because I told you we start with a basic classical simple Lie superalgebra, and finite dimensional simple Lie algebras by themselves are basic classical Lie superalgebra. Right? Finite dimensional simple Lie algebras are finite dimensional basic classical simple Lie superalgebra. For them, the odd part is 0.
Yes.
Okay.
But when you make affine Lie superalgebra, then you need like a modified Jacobi identity, right? So you said affine Lie algebra, so I was just confused. Like,
okay.
Is it affine Lie algebra or affine Lie superalgebra?
Okay.
And you also have with like finite dimensional simple Lie algebras.
Yeah. See, if you start with a G, this G is like this. Yeah. And G is a basic classical simple Lie superalgebra. Right? If G1 is 0, G equals G0 is just a finite dimensional simple Lie algebra. Now, if you make G hat is an affine, of course, untwisted. It's better to write it. Affine Lie superalgebra, but if G1 is 0, G hat is untwisted. define the algebra.
Okay.
Right?
Okay. There are no degree 1 elements, so
Yes,
the
exactly.
regular Jacobi identity works.
Yes, exactly.
Okay.
Okay. Right. Let's look at the first example. Suppose that n is a positive integer greater than 1 and set G to be a sum n f. And you remember it is all elements of the matrices S square n times n matrices, or the trace of x is 0. Okay, and you remember we had H, that is the set of all elements of G, where it is diagonal, right? And you remember again, G is direct sum G alpha when alpha is an element of R. And what was R? R was 0, epsilon I minus epsilon J when I is not J between 1 and n. And G0 is just H, and G epsilon I minus epsilon J is just F E I J, right?
So what have you written there? G, yeah.
G epsilon I minus epsilon J, it was F E I J.
Oh, okay.
Yeah, it is. Yeah. Okay. And now define this bilinear form from G times G to F maps xy to trace of the product of xy. And you can show that this bilinear form is a non-degenerate bilinear form, and it is symmetric. Symmetric and non-degenerate, right? And moreover, if we restrict it to H times H, it is again non-degenerate. Okay, and H is finite dimensional vector space, and we have a non-degenerate bilinear form on H. So we can define this T, or let me call it so, from H to H star, mapping H to form H blank, maps H to a functional of this form, right? And as this bilinear form is non-degenerate, this slope is 1-to-1. And as H is finite dimensional, we get dimension of H equals dimension of H star, and so it is an isomorphism, right? So for each lambda belonging to H star, there exists a unit C lambda belonging to H such that so H lambda equals lambda, right? And so we can define a bilinear form. I denoted again by this notation from H star times H star to F, mapping lambda mu to C lambda C mu, right? Okay.
And that is the old bilinear form, right?
Sorry?
On the right, that's the old bilinear
Yes,
form.
exactly.
Okay,
it is the bilinear form that we already have on H. And as an exercise, show that, remember, we have epsilon I belongs to H star. Yeah? So when we have epsilon I belongs to H star, we can talk about the form of epsilon I, epsilon J, right? And as an exercise, show that epsilon I is a positive integer. In fact, the form is a positive definite bilinear form on a span of R Q. Okay. Next, assume G is SL and MF when N is not equal M and both N and M are greater than 1. And you remember what was the definition? It was the set of all Banach matrices A, B, C, D, such that A is A times M, B is N times N, B is M times N, and C is N times N. And trace of A equals trace of B. In other words, the set of all elements such that supertrace of those metrics is 0. Right? Okay. And G is G0, direct sum G1. And you know G0, I don't want to write it again. You remember, G0 is the set of all matrices such that the off-diagonal blocks are 0. And for G1, G1 is the set of all block matrices with diagonal blocks are 0. So we have this G and set H to be the set of all elements of G such that X is diagonal. Okay, G is diagonal, and then we have G equals direct sum G alpha when alpha is an element of H star. Support of G is 0, epsilon I minus epsilon J, delta P minus delta Q, epsilon I minus delta P, when I is an element between 1 and m, and P is an element between 1 and m, and also the same for G and G. Okay, and again, you remember epsilon I was a functional mapping E11 plus E1 bar 1 bar to delta I1 maps ECT minus E11 to delta IT minus delta I1 and E P bar minus E1 bar 1 bar to 0. And the delta P is an element of H to F, mapping E11, E1 bar 1 bar to delta P1, ETT minus E11 to delta 0, and EQ bar Q bar minus E1 bar 1 bar to delta PQ minus delta P1. Okay. And now define this bilinear form from G times G to F, mapping xy to supertrace xy. X and Y are Banach matrices, so if we form xy, again we get a Banach matrix, and so we can talk about the supertrace of xy. And if we define this bilinear form, then you can show by yourself that this bilinear form satisfies this property. It is non-degenerate. It satisfies this property. And more importantly, the form restricted to H, again, is non-degenerate. Right? And again, as we have a non-degenerate bilinear form on H, and H is finite dimensional, we can transfer the form on H to a form on H star. Okay. The map, so from H to H star is a linear isomorphism. So for each lambda belonging to H star, there exists a unique T lambda belonging to H, such that so C lambda equals lambda. This allows us to define this binomial form from H star times H star to F, mapping lambda mu to C lambda C mu. And again, as we mentioned, this bilinear form is the old one, right? And now the differences are coming up here because you can show that exercise show that for each alpha belongs to epsilon I up to epsilon 1 up to epsilon n, the form alpha is positive, and for all beta belong to delta p, I mean delta 1 up to delta n, the form beta is negative, right? And you remember, in the previous example, I told you that the form restricted to S span of R over Q is positive definite. And here we don't have it. And also, we have some other relation that you can prove that alpha beta is 0. Yeah, it is true, but let me write it in this way. So all gamma belongs to epsilon I delta p, I between 1 and m, p between 1 and n, gamma is 0. In fact, in the super case, we have some elements which are self-orthogonal. We have some non-zero elements which are self-orthogonal. And it is something that does not happen for non-super case. It is this property just happens for the super case. But remember, we are talking about finite dimensional case, right? Okay, any question? If it is clear? Okay. And now let's look at the let's look at the Affine case. Assume G is SLF n is greater than 1, and form G hat, which is G. As I told you, when we are talking about affine the superalgebra, we assume that the F is C. So just to be it is just because of this tradition that I put C here. Form, yeah, we assume G is this, and form this G hat plus minus 1 direct sum CC, direct sum CD. Okay, and you remember G hat is direct sum G hat alpha when alpha is an element of R hat, in which R hat is R plus Z delta, and R is the root system of G. R is support of G. G is direct sum of G alpha. Alpha belongs to R. Oh, it's better to write this. Okay. All right. And we call that, we have a bilinear form from G times G to C maps xy to trace of xy and define this form. I denote it again by the same notation from G hat times G hat to C in this way. I define my G hat has 3 independent parts. So when I want to define this bilinear form, it is enough to define it in each part. I define C to be 0. I define DB to be 0, but CD to be 1, and C with everything to be 0. Right, and for each tensor Cn, y tensor Cm, I define the form to be delta n plus m0, the form of xy. Right, and D with which part? G, yeah, G tensor C plus minus 1. It is also 0. Right? We can define this bilinear form, and this bilinear form is a non-degenerate symmetric bilinear form, and the restriction of this form on the capital H is again non-degenerate. Is non-degenerate. Okay, and we can again say that we have a non-degenerate bilinear form on this finite dimensional edge, so we can transfer the form on H star as usual, and we can talk about the form of two elements of our hat. Okay, we can transfer the form on H to a form on H star in the natural way. Okay, let me denote the form also with a notation. On the form on H, we can transfer the form on H to a form on H star. And recall that R hat is R plus C delta. You remember what was delta? Yeah? And the last section.
Yes, I've written it down, but I don't remember.
Okay, okay. Let me tell you. Delta is a bilinear form from H to C. And this delta maps H direct from CC to 0 and maps delta to 1. Right? And you remember, I told you, whenever we have an element of this edge, this small edge, a star, if we have a functional on this edge, I can consider it as a functional on the capital edge because I can define the value of that functional on C and D to be 0, right? So for me, R hat that's written as R plus D delta is a subset of H star, right? And R hat is R plus the delta, and we have a bilinear form here, and you can show that delta is 0, right? And let me recall R. What was R? R was epsilon I minus epsilon J when I and J are not equal between 1 and n. Right? Okay. You can show that delta is 0. You can show that epsilon I minus epsilon J, epsilon I minus epsilon J is positive. And you can prove that delta epsilon I minus epsilon J is 0 for all I and J. Right? Look at this. We have some self-orthogonal element here, but this orthogonal element is orthogonal to all other elements. Yeah? But in the finite case, in the super case, we have some orthogonal elements, but those orthogonal elements are not orthogonal to entire system. It is something that happens for Affine case. In Affine case, we have some elements which are self-orthogonal, and this self-orthogonal element is orthogonal to all other elements. Right? Okay, if you have any question, please ask.
And this happens both for the case of affine Lie algebra and affine.
Okay, let's look at another example.
Okay.
Yeah.
So this is just for affine Lie algebra.
Yeah.
Okay.
Oh, Okay. And example, suppose that G is SO, F, and M, and N are greater than 1, and N is not F. Okay, I need some chart. Okay. Again, for the affine, the superalgebra G hat, G tensor C. Okay, again, I was assumed to take C as my field. C plus minus 1 direct sum C direct sum CD. Then G hat is direct sum of G hat gamma when gamma is an element of H star, where H is H direct sum CC direct sum CD. Support of G hat is R plus Z delta. Delta is defined as in the previous case, and R is just 0 epsilon I minus epsilon J, delta P minus delta Q, and plus minus epsilon I minus delta P, when I and J are elements between 1 and n, and P and Q are elements between 1 and n. Okay, and again, we can define the bilinear form as in the previous case on this G hat. Recall this bilinear form from G times G to C maps xy to supertrace of xy, right? And we find this bilinear form from G hat times G hat to C. The definition is exactly as in the previous case, right? In fact, X tensor Cn, Y tensor Cm is defined to be delta n plus minus delta n plus m0 xy. Okay, let's check it in the previous example. I wrote it in this way, right? N plus m0. Yeah, I just wanted to be sure. Okay, delta n plus m0 xy, and C with everything is 0. D with itself is 0, and D with G tensor C plus minus 1 is 0, and CD is 1. And again, this is a bilinear form. This bilinear form is supersymmetric. Is supersymmetric in the sense that y equals -1 degree x degree y, yx for all xy belong to g hat, 0 union g hat 1. Okay, and the restriction of this bilinear form to H is not degenerate, and we have the same story as before. We can transfer the form on H to a form on H star. On H star, and now, okay, so that delta is 0. I recall that R hat is R plus Z delta. Show that delta is 0. Show that epsilon I minus epsilon j, epsilon I minus epsilon j is positive. Delta P minus delta Q, delta P minus delta Q is negative. Show that epsilon I minus delta P, epsilon I minus delta P is 0. And delta with everything is 0. Okay? In fact, we have R hat equals R hat real union R hat ns union R hat imaginary. By R hat real, we mean 0 and all alpha belongs to R hat, such that alpha is not 0. If we put 0 here, some people prefer to separate 0, but for me, I always consider 0 as an element of R real cross, R real hat, R ns hat, and so on. And R hat ns is indicated for non-singular is 0. And let's first define this one. R hat imaginary is all alpha belongs to R hat, such that alpha with everything is 0. And in fact, it is Z delta. And R hat and S is the other elements. R hat and S is the set of all elements. I put 0 as well. Alpha belongs to R hat minus R hat imaginary such that alpha is 0. We have three kinds of elements. Some elements are not self-orthogonal. We call them real. Some elements are orthogonal to every other element. Okay, we call them imaginary. And we have another kind of roots which are self-orthogonal, but they are not orthogonal to entire root system, right? And again, you can see that the only difference between the super case and non-super case in affine setting is the existence of these elements. We have some elements which are self-orthogonal, but they are not orthogonal.
Also, negative.
Yes. But in a sense that we just consider it as they are not self-orthogonal, it's the same. You are right. They are.
What does that notation mean? The last one, NS. Yeah, I don't understand.
R hat imaginary.
Yes.
I call them imaginary, and they are orthogonal to all other elements.
Okay. Mm-hmm. Now, what does that notation mean? I don't read.
I didn't get what this one.
No. After that, what's
this one?
Yeah.
This vertical one.
Yes.
Such that it is just an element such that some condition.
Yes, but okay. So what you're saying there is zero is contained in NS, alpha in R hat.
Yes.
Such that.
Alpha is an element of R hat, but not an element of R hat.
Okay,
it is set minus.
Okay, so minus.
Yeah. It is set minus.
Yes. Sorry.
No problem. Let me write it in a better way. That's right now.
Thank you.
You're welcome. Okay, and exactly because of the existence of these elements, the representation theory of supercase and non-supercase is completely different, just because of the existence of this kind of elements. Okay, and it was the last lecture, and I think it's better to stop it now. Okay, and thank you, everybody. Have a very good weekend for everybody, for you and for you. Okay.